Hello, am I audible?
Yes, sir, you are.
Okay, perfect. Okay, so there are two people who are here from the AS class that I just took. So I'll be going through the introduction part once again. Okay, so let me share my screen and let me know if you can see it. 1 second. All right, so is my screen visible?
Yes, sir.
Yes, sir. It's
Okay, perfect. Okay, so this will be an A2 level physics class, right? And we'll be following the topics that are specifically in the A2 level syllabus. So I'll start by introducing myself. My name is Basil Abdul Majid. I'll just write it down over here. And I am a physics graduate, theoretical physics graduate from NUST in Pakistan. I have also worked in NUST in the physics department recently as a graduate teaching assistant, where I have been conducting problem solving sessions. We call them recitation sessions, and teaching some classes and all. So I also have approximately of a 5 years of teaching experience as well. I just use T.E for teaching experience. Right. So I'll start by basically telling you about, this is a demo lecture, and so we'll start by getting to know each other and everything. So I'll start by telling you where did my physics journey begin? Why did I even choose to pursue physics in the first place? It really started when I was I was finishing my O levels and I was about to start my A levels. I did my A levels, O levels, and most of my education except from university education. I did it from Saudi, KSA, and so my interest in physics basically developed because I was randomly watching videos on YouTube, and I came across this documentary of Sir Isaac Newton, and I was intrigued by the documentary, and so that basically took me to even more videos. So it went on to Albert Einstein and so on, right? So that's where it started from. I started reading popular books, science books, and but eventually you see that you don't have everything that is covered in those popular science books. So what you do is you read them, you get interested, and then when you start doing physics for real, I mean, you get into its technicality, and to be honest, without mathematics you cannot do physics at all. So in those science books, it's just mostly philosophical things in those popular science books. Anyway, so that's where it started from, and then I started my degree in computer engineering from GK, but unfortunately that happened because my parents, they wanted me to pursue engineering, but I left that. 1 year I stayed there. I did 1 year of computer engineering, and then I left, and I came to NUST to pursue theoretical physics. Anyways, that's this, and my research interests are in quantum field theories mainly, but you can include string field theories and general relativity, gauge theories of gravity, and so on. So that's what I have recently also been working on. I've been working on general relativity as a quantum field theory, but these things might go over your head. I'm just using some fancy names. So, sometimes some people like fancy names, and it sparks the interest of a person. Anyways, I would also like to hear from you all. Where are you from? When are you taking your session? This A2 physics session, is it October, November this year, or next year, May, June? And what time zones are you from, and everything? So you can speak up now.
Assalamu alaikum, sir.
Walaikum salam.
Sir, I'm from Karachi. I'm opting for physics in May, June 2023.
Right. Okay, amazing. So what's your name? I cannot, like on the screen, I cannot see who's speaking right now.
Omar, sir.
Oh, right. Okay. Amazing. Nice. Okay. So any more volunteers who would like to speak up? Also, I would like to know your interest in physics. Are you passionate about it? Or you avoid it? Some people they find physics really hard. Some people find it really easy as well. So, are you passionate about physics? Do you? What are your feelings towards physics?
Sometimes it is easy and sometimes very difficult.
Right. Okay. So, okay. So yeah, it's like that. It's like that sometimes. The problem with physics is, I'll tell you, to be honest, is that you have to think a lot. You have to imagine things, and it basically requires imagination, and a lot of imagination. And some people find that very easy to imagine things. Some people some of them, they don't even have the time to think about these things. Anyway, let's talk a bit more about this. Okay, so we'll first let me just first write down this the pattern that we'll be following, how we'll be going along our lectures and everything. So we'll be doing this that from Monday to Thursday will be mainly focused towards the theoretical or theory part of, or the conceptual part, you can say, of your course. And of course, we'll be doing examples. We'll be solving some problems and all. So that's what we would be doing. We'll be doing in from Monday to Thursday. On Friday, specifically, I would be we'll keep this for questions, right? So what I mean by this is, I'll be answering your questions. We'll be doing past papers on Friday. We'll be focused on past papers. And so what will happen is that when we are doing this Monday to Thursday, we are doing lectures, we are doing some problems and everything. And of course, you'll have some questions. And maybe not during the lecture, maybe, and definitely maybe also during the lecture. And you can stop me and you can ask your questions anytime that you feel that you don't understand something. You can stop me right there and you can ask your questions. Suppose that you have asked your questions and everything, and then later on when you go through your notes again and you look at your concepts again, and then you have some questions, more questions. So you can note them down. You can post them in the WhatsApp group as well. For example, let's say you're solving a problem and you have a problem in that problem basically. But so you can just share that question on WhatsApp group, right? And so try to do it before Friday, so that I'll have the time to go through those questions, and then we'll sit down and we'll solve or discuss them on Friday, the class that we will have on Friday. Right, so that's this. And questions are very important. You have to ask questions, don't hesitate. Nobody's judging you over here. Whatever problem that you have, feel free, be open, and just fire away, right? So again, my way of teaching is that I like to become a student with all my students, and then look at things from their point of view. Because if I am a student in this class, what I'll be doing is I'll understand where you might be having problems, what things I should elaborate more on, and your questions would be more understandable to me in that way. So that's how I like to do it. Right, so that's this. Any questions so far from whatever we have discussed right now? Anything that you have to add to it, or maybe you're confused, or you want to ask something?
No, sir.
Okay, great. So right. Okay, so at this point, there is this problem in this Zoom. I don't have this access to host this meetings for more than 40 or 45 minutes, I think it is. So hopefully this problem will get resolved by tomorrow, and we can pick up the pace, and we'll start with chapter 1 properly, which is of motion in a circle, I think, right? Circular motion, basically. So what we can do is we can start the topic right now. But before I go into that, I think I have already asked you this, right? If do you find physics boring? Any of you? Any of you who thinks it's just boring, or like it's just too many equations, and like it goes above my head completely? Okay, nothing. Okay, so what I wanted to do was I was going to describe some frameworks in which we do physics, and the one that you are studying right now, it's more or less, it's just Newtonian mechanics. And then there are more frameworks as well. We'll start it in this way, that we have a Newtonian mechanics is a framework in which you can do physics. So it's a very basic and a very limited framework, where you use your Newton's laws, and you solve your systems. But it's a very limited framework. Let me give you an example. Suppose that if your speeds are approximately close to the speed of light, that's where Newtonian mechanics fails, and it has no real answer to that problem. So that's when we use something else, another framework, and that's special relativity. Now, special relativity is a framework that allows calculations. You can calculate, and you can work with physics of particles that are moving at or very close to the speed of light. Right. And then what is another thing that you can have? we have atoms, we have electrons, we have subatomic particles. And those particles cannot be described as well properly using Newtonian mechanics. You need something else, and that something else is quantum mechanics. I don't know if you have heard the name. It's actually, you might know quantum physics, and quantum mechanics is just the same thing, quantum physics. And you use quantum mechanics to describe the world or the universe of very small. And so there is always a correspondence principle, you can say, which can take you from SR back to Newtonian mechanics. And that correspondence principle for this case, from going from SR to Newtonian mechanics, is when your speeds are smaller than the speed of light. That's when you can go back to Newtonian mechanics, and you can use the Newtonian mechanics framework without any problem whatsoever, right? And similarly, for quantum mechanics, you can go to Newtonian mechanics if your well, there are many ways to state this. I'll just state it in something that you will understand more. When the size of your particles is large, so you can use Newtonian framework. What about the fact that if your particles are very small and they are moving with a very fast speeds, so their speeds are approximately closer to the speed of light? That's when you need another framework, and that is called quantum field theory. And so this is basically combining quantum mechanics and special relativity, and it's actually even a very it's kind of, you can say it's a recent theory, or it's a recent framework in which we work. Anyways, so what we will be, or what you focus more on in your AS O levels and A2 physics is Newtonian mechanics. And then you go to your university, and if you're even if you're doing any pre-engineering course, or you're doing engineering in your university, or you're doing mathematics or physics, for example, you take very basic courses in the first semester. You take the course of mechanics, or sometimes it's called applied physics, and you use Newtonian mechanics for the most part of it. And then you go, if your career, if your education is in physics itself, it's deep focused in physics, so you're doing a degree in physics, then you move into these things. You learn about special relativity, quantum mechanics, and if you want to, you can also pick a course of quantum field theory. And so these are, what you're doing right now, Newtonian mechanics, it's a very limited framework. And so if you want to learn about things more deeply, and understand things in a much more real life situation way, then you need to understand special relativity, quantum mechanics, and then even quantum field theory, and so on. Anyways, this was just me telling you about some trying to get you interested into physics. I guess what we should do from this point now is, let's start with the first chapter of A2 physics. Wait 1 second. Okay, perfect. So before I do this, again, I'd like to ask you if there is any question. Up until now, any question? I don't think we really did not go into the chapter or the course specifically, so there might not be any questions. But if there is, you can ask, right? So anyways, let's start with the first chapter of A2 physics, which is chapter 6 of your textbook, and that's motion in a circle. So Well, basically, we discuss in this the kinematics of our circular motion, uniform circular motion. We will talk about centripetal accelerations. We'll talk about centripetal forces, and it's more focused only towards you have something that is moving in a circle, and what's keeping this ball, or you can say a particle, what's keeping it in this motion? It's what's keeping it in moving in a circle. So we'll need some quantities. We'll need some things to study this kind of kinematics. And so we'll start with something that is called the angular displacement. And angular displacement, we'll use the appropriate units to represent angular displacement or angles, is radians. Now, radians is just an SI unit for your measuring angle. And so suppose if your angle is theta, then you can also relate, there should always be, if you're, so for example, let me give you an example. If you're using kilograms and grams, so there is always a relation from going from kilograms to grams and then from grams to kilograms. Similarly, if you're using the radians unit for angle, then you should be able to relate it to the degrees unit for the angle. And it's done so by that in one complete revolution, an object rotates through 360 degrees or 2 pi radians, which just means that pi radians, it's pi rad, is equal to 180 degrees, right? So, okay, can you tell me if there is, you have this thing where it says this much time is left for the meeting?
Not yet.
You cannot see the time of meeting? How much time is left? Okay.
Already 25 minutes gone. That means around 15 minutes left.
Right. Okay. Okay. So, right. So we have pi radians is 180 degrees. So that's the relationship between radians and degrees. So we have that when an object is moving in an angle with respect to the center of the rotation, the angle theta is known as the angular displacement. So what that means is you have, so something is bound to this center point, right? And it's moving about this center, so it will move like this. So suppose that this is your reference line, and you measure the angle from this reference line. So whatever distance that this moves in this direction, right? You can measure the angle from this reference line, and that would be the angular displacement of this ball that is moving. So let's call it a ball, or let's call it a particle, whatever, right? So that's your angular displacement. That's how an angular displacement is defined. So if I have something that's defined as angular displacement, then I can define what is called the angular velocity. So it is how fast does your displacement changes, the angular displacement. How fast does the angular displacement changes is called the angular velocity, omega. And it's represented with omega, where you can mathematically write it as the ratio of your angular displacement to time. Now, if you have a one complete revolution, which just means that suppose it starts from this point A and it moves in a circle and it comes back to this point A, then that's one complete revolution. And for that, the angular velocity is defined as 2 pi over t, where t is the time period. And the fact that we have this time period over here, it comes from this thing that time period is basically defined as the time it takes for your body to complete one complete revolution, which was defined over here, right? So starting from one point and coming back to that point in a circle is defined as a complete revolution. Right. So next we have a linear velocity. Now, what is linear velocity? If you have something that is moving in a circle, so something is keeping this particle moving in a circle. So let's just try to draw it over here. And suppose at this point, suppose that there is some string that is attached to this ball or a particle, and it's keeping it moving in a circle. What if this string goes away? The string vanishes. What would happen at that point? Suppose that it was moving in this direction. Can you tell me what would happen if I just remove the string or someone just cuts the string off? What would happen to this particle?
It will no longer move in a circular motion.
Yeah, but what would be its behavior then? As soon as I cut this, where does this particle go? Will it fall back to the ground or what? Anything you can say, even if your answer is wrong. Nobody's judging you here, right? Nobody's judging anyone here. If your answer is wrong, you'll learn something. You might have the correct answer in your head and you're just not saying it. So just say whatever is in your mind. What do you think would happen to this ball?
It would go
Like I
flying,
said, it would go
flying away.
Yeah, exactly. So it would go flying. So it would go in this direction, and this let me just draw it properly. So it would, if it were moving like this in this direction, right? If it were moving like this, then the tangential component is this thing, right? So it would go straight in this direction. So now if it were at this point and then the string was cut, then the string was cut, and again we know that it's moving anti-clockwise. So what would happen? It would go flying in this direction if I cut the string off. So with which velocity does it go flying in this direction is known as the linear velocity, and it's represented with v. So that's the linear velocity. And it is also, you can use the word instantaneous velocity at any point on this circle, because as soon as you cut that string off, with that particular velocity, it would go flying off in the direction corresponding to the which direction it was already moving in the angular velocity. So is this thing clear? Is the linear velocity, do you understand what linear velocity is? Or is there any question?
No, sir.
Right, okay. So linear velocity, it is defined mathematically as the arc length over time that it takes to move to that point, right? So we have this thing, we have v, linear velocity. It is defined as, why am I writing it down? It's mentioned over here already. So it's the arc length, and we know from from mathematics that arc length is simply r times theta. Do you have any problem in understanding what arc length is, or do you know what an arc length is? It's just so suppose you have this angle theta over here, and this is the arc that it forms, and so the length of this region is the arc length. And you can find that by simply multiplying this length with the angle theta. And so if this length is r, then you have r times theta as this, the length of this arc. Right? So what happens, why is it arc length over time taken? The reason for that is because if it was moving in some direction, right? So what you do is, suppose it's at this point, and initially just before that it was at this point. So what happened is, it would have the velocity that it would have had between these 2 points, this region. So what you do is, the time it takes for this particle to move from here to here, where you just cut this string off, is the time taken, and the length of this path was the arc length of this circle, which is r theta. So that gives you r theta over t, which is basically r times omega. And the reason for that is because theta over t was defined as omega, where omega is the angular velocity. So you can even write, so you can write down your linear velocity in terms of your angular velocity, which you should not be surprised. It should have been possible because it was already related. The linear velocity was related to the angular velocity.
Sir, can you explain it again?
Yeah, of course I can. Which part are you talking about?
Sir, the formula.
Oh, right. So why is it like this? Well, so you have to imagine, right? So suppose that you have some string attached to a particle or a ball, and you're moving it in a circle. When you break the string, what happens is, you have to consider this, some change in angle, change in theta. You have to consider some infinitesimal, you can say infinitesimal area or infinitesimal length, which means that very small. So what was happening just before I cut the string, and right at the moment I cut the string? So that's this length over here, which is your arc length basically. And the length of this string is basically the radius of the circle that when you are moving your string or the object in a circle. That's r. And the angular displacement just before and right at the moment when you cut the string is this theta. So this gives you this length, which is r times theta. And I want to find the velocity of how fast did this point move to this point. So this point, how fast did this point move to that point? So I'll just take this length that it covered divided by the time that it took to cover that length. So that is this linear velocity. Is it any better now?
Yes, sir.
Okay, right, perfect. Perfect. So I got this notification a couple of minutes ago that this meeting will end in 10 minutes apparently. Okay, do you see the time that is remaining?
Yes, 2 minutes and 54 seconds.
Right, so yeah, so we have around 3 minutes left. So okay, so is there any question from whatever we have discussed so far?
No
Right,
questions.
okay, so now I've already explained this thing to you, that the direction of the linear velocity is tangent to the circle, right? You can see that because when I drew this thing, so this was just a tangent at this point where the object was. This line was a tangent to that point, and this tangent vector is defined as the linear velocity of this object at that particular point. And because it's defined using this tangential vector, it's also referred to as a tangential velocity. Right? So these terms, they're just the same thing, right? Tangential velocity and linear velocity is exactly the same thing. Okay, so right. Now, if you look, even if you look at this expression for omega, which is angular velocity, and for v, which is the linear velocity, you can immediately tell that this thing omega, the angular velocity, at every point on your circle would remain constant, right? So if it was moving in this, if it was at this point at some time, or if this ball was at this point at some time, the angular velocity remains constant, right? You can look at this expression and you can tell that. But what if I consider the linear velocity? Now, linear velocity is clearly, if I have points that are away from this axis, this line. So for example, the length of the string gets larger, right? What happens then? Then I cannot draw it properly over here, but this is still moving in a circle, and the length of the string is now some r prime. What happens then? The tangential velocity would increase, and you can see that from this expression, because the tangential velocity is proportional to the radius r. So if I increase the length of my string, then the linear velocity would increase. So what is happening is that if I use a longer